Welcome back, static students. This is ENGR 214 ampersand, Bellingham Technical College, winter 2020. This is the last of our recorded lectures on truss analysis. This is the method of sections in which we will have a shortcut to getting the force in not the whole truss, but maybe one or two members. We'll do this by cutting the truss virtually, representing the forces on the cut section as just named forces in those members going in the direction of the members because they're two force members, and then taking both of those cut sections and placing each one in static equilibrium. So we'll end up with two FBDs instead of one whole truss FBD. Compared to the method of joints, this method is faster and it's much easier for determining the force in a particular member. We don't need to solve the whole truss, so that's the big advantage over method of joints. So we'll go through the step-by-step way to go about this. Again, this is just another application of putting things in static equilibrium and leveraging the fact that a truss has nothing but two force members. So we know the direction of any force that's being applied by that member. We know that whatever magnitude that force is and whatever direction it's in, it will be oriented in the same orientation as the member. So we're going to leverage that a lot in this method. We leveraged it in the method of joints, but we're really going to see it here. So we start by solving the whole truss FBD to find the support reactions. If we have an extra support reaction, we may not be able to get all of them, but certainly if it's simply supported, we'll get all three if it's a plain truss. More obviously if it's a space truss. And here's the next step. Here's the critical step. We're going to virtually cut the truss into two separate pieces with a cut passing through the member of interest. So you have to cut through the member you're looking for if you're only looking for one member. Then you're going to leverage the fact that a truss is only made of two force members by representing the forces from the opposing section, the section you cut away, as force vectors that are automatically aligned in the direction of the truss members, since truss members are two force members. So that's it. That's the whole method. So to make it real, we're going to just step through one example. This is example 4.4. So we have a little bit bigger truss. A little more elegant, pretty design here because they have two levels, a little bit higher in the middle. This is a Pratt or a Warren or one of the classic truss styles. So let's look at the support reactions. We've got two potential forces here and one here. It's 2D, so it is simply supported. There's three support reactions. Let's take a quick moment to apply what we knew about truss determinacy and rigidity before we dive in. This is an example, so we can be pretty sure that it's probably statically determinate, but you never know. You might get a colleague or a boss or an evil instructor might give you an indeterminate truss or a non-rigid truss. So let's start by, now that we know the number of support reactions is 3, we should be able to say that twice the number of pins minus 3 should be the number of members. So let's do a quick count just to make sure. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 pins. That means we'll have 18 independent equations of equilibrium. Subtract 3, we should have 16 members. So we got here starting with AB is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Did we miss one with 16? Let's do another count. We'll start at the bottom here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Aha! Okay. So that's not necessarily adding up. Did we do our math right? Is 18 minus 3 equal to 15? Okay. Nothing like an arithmetic error first thing in the morning to start your day. So this is rigid and statically determinate. So a good check and a good exercise, and a good exercise in arithmetic on the fly. We'll have a little bit of trig to get our angles for the forces on the cut section. So I won't be walking through the trigonometric solutions to get these angles. I'll trust that you guys at this point can do that just based on these dimensions. Okay, so we're going to start with our step one, solve the whole truss FBD. So I'm going to make the whole truss one big rigid body, which I've represented with a big blob to keep myself in check there. And I'm going to have support reaction A, two forces, A sub x and A sub y. I'll have a force at point F that I'm representing by R. And I'm going to put all of my applied forces. So I have 2 kilonewtons at D, and then I have a 1 kilonewton at I, a 1.5 kilonewton coming from H, and then I have 3 kilonewtons at G. So I have included only the dimensions that I need to put this in static equilibrium and calculate moments and forces. So some of the forces in the X, I know that A sub x is going to have to be pointing in the direction given with 2 kilonewtons to balance the applied load. The sum of the forces in the Y says that A sub y plus R minus all of the applied vertical loads is going to have to be equal to 0. And I can sum the moments about point A. And again, you'll notice I'm always summing the moments about those hinge points. And I hope you remember that the reason for that is that eliminates two variables, usually makes it possible for me to get a numerical value for the remaining support reaction in one go. So in this case, I do that, and then I get a value for R of 3.92 kilonewtons in the direction shown, and then I plug that back into my sum of the forces in the Y, and get a value for A sub y. So now we have the support reactions, we have the applied loads, and now I'm going to look back at my truss and go, which member was I looking for the forces in? Find the force in member GH. Why GH is important, we don't know. Maybe we found out that somebody built it with a substandard material, or maybe somebody is out and inspecting this truss. Maybe it's being used out of doors and someone found an excessive amount of corrosion. Maybe somebody's looking at lightweighting and for whatever reason felt that that was critical and wants to see if we could reduce the cross section. I don't know, but those are some plausible reasons why you might be interested in GH and not necessarily interested in finding the loads carried by all the truss members. Probably, I would think that an inspection finding might be something that would alert you to needing just one member. Okay, so we need to put our section, our virtual cut through GH, but we have to put it through enough other members to literally separate the truss into two pieces. So I'm going to choose to put my cut here. I'm going to come up and I'm going to cut through GH, and then I'm going to also cut through DG and DE. So this little squiggly line here is my cut. So I'm going to separate the truss into two pieces along this line. And as a result, I'm going to isolate that bottom corner. So I've placed my cut, and now I'm going to look at this remaining, this right-hand side. And anytime I have cut a member, I no longer have a member, but I have a force that is being directed along the member orientation and in the direction that it would be, which we may or may not know. So we can make some guesses though. So here is an FBD of the right-hand section, FBD right-hand section. So you can see I don't have a lot of the intact truss here, but I do have one triangle. I have the right-hand support reaction. I have one applied load, and then I have 1, 2, 3 unknown forces representing the force in members DE, DG, and HG, and I have their orientations because I can use the truss geometry to get the angles phi and theta. Well, I have three unknowns. I now have something that I am going to put into static equilibrium, and I now have an equation for moment that is applicable. I need to have this whole truss body not rotate. So I have three equations of equilibrium now. I'm back to more of my classic equilibrium analysis. I have the geometry, I have the orientation of the forces. I don't know their direction. In other words, the magnitudes could be positive or negative, but I know the direction of orientation. Three equations and three unknowns. I'm ready to go. Now I'm back to just a standard old statics problem that I can solve. And in solving it, I will get all three of these numbers, including the one I want. And so that's how you proceed. And just to compare with the method of joints, I still have to solve three equations. So I've still got three unknowns, but had I gone through the method of joints, I would have had the same whole truss analysis to get the supports, and then to get to member GH, at best, I would have had to go through 1, 2, 3, probably 4, 5, maybe 6 equations, 5 or 6, with 6 equilibrium analyses, 6 joints, each of which would have 2 equations. So this is definitely a shortcut. So just to walk through it, I carried down the geometry of the whole truss and gave myself theta and phi at 18.43 and 69.44 degrees respectively. So that gives me the orientation of DG and DE versus the horizontal and vertical. So now I'm using a standard horizontal vertical I and J coordinate system here, just like we would with any kind of equilibrium analysis. I can sum the forces in the x, assuming that the positive x-axis is to the right and the positive y-axis is vertically upwards, it's up towards the top of the page. So I have negative hg minus dg cosine phi minus dE sine theta, and nothing here. Oh, sorry. Theta is defined as the other angle, so it's minus cosine theta. Apologies. I was thinking I'd defined it up here. It's actually defined, theta in this case is defined, there's a little arrow, it's defined as the angle to the horizontal, not to the vertical. That's drawn somewhat misleadingly. Apologies. And we can tell that because we're taking the cosine. Okay, so there's our sum in the x. Sum in the y, we'll have now the sine theta component of dE going upwards. We have the sine component of dg, sine phi, and then we'll subtract 3 kilonewtons for an applied load, and we'll add 3.92 kilonewtons for our right-handmost support reaction. Hg is horizontal. For moment, I chose to take moment about point G because in so doing I could eliminate the forces for member DG and HG, and then I could get one of those three immediately. And so we did that and had to use a little bit of geometry to get the moment due to DE about point G. It had a couple of components, but that's basically vector resolution and R cross F in one form or another, and was able to solve for DE. We found that it was in compression, so we got a negative sign for the way it was drawn. It was drawn as if it were in tension. It was negative, so we found that that was in fact in compression. Then fed this number back into our X and Y equilibrium expressions and turn the crank. Now we went to 2 equations and 2 unknowns, solve for DG, and then solve for HG, and found that HG was in fact in tension, 3.28 kilonewtons. Now you'll notice that we could go and apply those values to the other section, and then make sure it's in static equilibrium given whatever applied loads it has and the support reaction. That would form kind of a pseudo check. So we can always use the other section for a check. I did not choose to go do that because I had the answers. This was an example in my book. But if you were uncertain or you wanted to be absolutely sure of your answer, that would be another way to do a check. It's not an absolute check the way we had in the method of joints necessarily, because we might have some applied loads in that other section that it's possible to forget to apply. But it does just give you another way of error checking that you didn't take a sine or a cosine incorrectly on a calculation. So that is it for this lecture. This was our one example of method of sections. There are some efficiencies with how you take your section to reduce the number of equations as much as possible. That's something that I will refer you to a good statics book if you have one. I pick up on this in your quiz, but generally, just like method of joints, you will get better with practice, and a lot of things will be obvious as you do it more and more. What is the most efficient way to take a section? Probably one of the biggest things to remember is quite often your moment equation, being most information rich, is going to be your best bet for determining the force in your member of choice that you need to solve for with the least number of mathematical steps. So if you think about placing your section in such a place that you will be taking a moment analysis of the resultant section, that will usually lead you to the best placement of sections for your analysis ease. Otherwise, as long as you cut it, you will be able to crank through your equations of equilibrium and get to it eventually. So that is now it for our discussions of trusses. At this point, the ball is in your court to practice. The more you practice, the more efficient you'll get. And you can see that all we've done is apply the conditions of equilibrium with some shortcuts, with some understanding of 2 force members and 0 force members. But otherwise, this is truly nothing new. But when it's all put together, it's very gratifying that you can make something that has immediate structural applications in our world just by applying what's really the simplest aspects of simple equations of equilibrium. So next up, we will have a lecture on internal forces, which is our lead-in to analysis of continuous internal forces in beams. So these are the shear and bending moment diagrams that you may have heard of that are used for beam analysis, specifically to find points of maximum shear and maximum moment within a beam that has complex loading. So we're going to actually swing completely to the other end and go from trusses that only have 2 force members to beams which for the most part exist to carry shear and moment, which are definitely render them not 2 force members. So we'll see you for that discussion next, internal forces, and then we'll jump into shear and bending. See you then.